Okay. Okay, so the majority of this class is celebrating Diwali yesterday, and so the rest of you come along for the ride. It's a festival of lights in India, and we normally make raspberry bars in India, I believe. But anyway, you guys don't say anything else. But anyway, so we are going to be talking about um, the factored approaches to reinforcement learning. Um, and a couple of things I actually am trying to remember, trying to get this clear something. I sent a mail to you about the need to read up, listen to or watch two videos on the Bayes networks. And that the next class, basically, I would be taking questions mostly. It will be more of a discussion rather than representing the entire Bayes network inference approaches. And then when we come back, we will be, which would be Thursday. So of course, next class I will be here, and as I said, it will be just a shorter class. We'll end at 4 o'clock, and then on the Thursday after that, we will start talking about learning Bayes networks, basically. So the first part is just get representation of Bayes networks and understand the inference procedures for Bayes networks. In particular, there are lots and lots of inference procedures, but the one that I just mostly discussed in those two videos was Markov chain Monte Carlo, which is sort of an approximate sampling-based approach. Okay. I also said that you can actually watch 8 videos instead of those 2 from 471, and that would give you a lot more background in basically probabilistic reasoning and Bayes networks. If you did not have much of a background in Bayes networks at all before, you might want to do that. This is just to bring everybody up to the same speed, these 2 ones. Okay. I also sent a mail about the PalmDP homework, right? So that one problem has already been released. You should start. You may as well do it before you forget PalmDPs. And then I'm likely to add a couple more problems on Bayes networks, and then that would be the homework 3. And it's not going to be, it's going to be added problem by problem. And then when the last problem is added, we'll basically give you very short time to be done with it. So if you wait until all the problems are added and then start doing it, then you take your own risk. Okay, so that's we have about a month before the semester ends, and then we have, this semester, I guess, every possible holiday was granted to us, including, I guess, Veterans Day as well as Thanksgiving. So there are actually not as many classes. So you should be, you should make sure that do the homeworks as and when they're given. And then the last thing is, actually, I'm just about to send you guys an email on the last project, which is basically sort of a simple project on applying latent Dirichlet allocation to some text processing task, okay, text mining task. And I will send you the description. I understand that we would not be talking about LDA until a couple of classes down the line, maybe several classes down the line. But in some sense, we have to parallelize it. You start actually, to actually do the project itself or get started with the project, you don't really need to know that much about LDA. But to understand what those results are saying and why you are getting those results, it would be helpful to have the LDA background. And so that's what we'll do. I'll just go ahead and give the project basically this evening. I'll just send you a link to it. And then, so you will have essentially until the end of the semester to complete that. Okay, that's like the third mini project. Okay, and then as I said, you also are asynchronously doing the reviewing stuff. Okay, questions? Okay, so what I am planning to do today is essentially I wanted to do a little on factored Q learning, even though so basically factored reinforcement learning. If you remember, actually, this is if we can go quickly back. Yeah, so this is where we were last time, right? So that you can have the value and policy functions can be represented in, for example, the value functions can be represented as decision trees or algebraic decision diagrams, and rewards can be represented that way. So can the values. Okay. You can also represent them actually as sort of arbitrary functions over features, because it's just a real number. Value and reward are real numbers. Okay, they take some features of the state and give a number out. Okay, so it's really a question of how do you represent the function. Okay, in this case we were using decision trees to represent the function in the most I guess without these approaches tend to be lossless. That's actually an interesting point to keep in mind. So these tend to be lossless representations. Basically, you would look at, if you are not given any of these representations, all you have is like a big table, right? The table state and the reward or value. That's the extensional representation of the function, okay? And what we are trying to do is provide a parameterized representation for the function, a more compact representation for the function, okay? ADDs basically try to look for any obvious structure in this particular extensional representation, and then wind up writing them as like things like this. For example, this, is an ADD that's telling you, what you would get as the reward under what states. So it's asking 20 questions. So, consider this state variable. If it is true, then consider this state variable. If this is true, then consider this, and then consider this, and then if it is false, then you'll get -7 as the reward. So I'm just trying to find a way of converting a discrete valued, a discrete function, discrete real valued function into a decision tree. Okay. Those of you who know decision tree based machine learning basically know that the only difference here is in the decision tree learning, these will all be trues and falses. So they're just Boolean values. Here, these are any numbers. You see what I'm saying? Okay, so we looked at that representation, and we actually talked about the fact that much of the art of doing these value and policy iteration using these representations involves essentially directly manipulating, given the ADD corresponding to the value function. Okay, you essentially take the entire value function to the next level by looking at one Bellman update, and that Bellman update is in essence done at all the states at the same time. Okay, so that's basically the factored representation and the algorithms based on factored representations. Now, in this case, the factored representation happened to be ADDs, and what I want to look at. And then we also talked about the fact that the factored representation for the actions in the MDPs tended to be either probabilistic strips operators or the dynamic Bayes networks. Okay. Now, in fact, one of the big things we did in this class is to see that really MDP and RL, they're extremely closely connected. Reinforcement learning and MDP have been extremely closely connected, right? In fact, reinforcement learning is nothing but MDPs with missing model. Okay, so you would think that while, of course, in the reinforcement learning, you are not only using the current model, you are also essentially learning about parts of the model, that you don't know of upfront. Okay, so other than that one aspect, the representation should not have changed much at all. However, you tend to see almost a dichotomy that many MDP approaches for factored representations tend to use these kinds of probabilistic strips operators and ADD style representations, while the reinforcement learning approaches tend to use linear functional representation, linear functional representations of values and rewards. Okay, so I'll show you what that is in a bit. Okay, one interesting question is you could have used that. So I will be talking about that representation and the interesting issues that come in actually doing reinforcement learning. But as I'm discussing that, I want you to keep in mind why couldn't I have used the representation of ADDs instead of the basically linear weighted summation of features representation. You could actually, it's just that the learning techniques will change different. Okay. So anyway, so what is the issue in reinforcement learning scenario? In the case of MDPs, the model is completely given. It's just a question of writing it more compactly. In the case of reinforcement learning, you're not given model, and as you act, you are learning pieces and pieces of the model. The normal reinforcement learning, basically every step tends to only update the values of some of the states. Right? In the TD or the Q learning, you basically update just a small set of states. Values are updated based on the reward you got when you actually acted in the world. Okay. What we would like to do is somehow from from just a few executions, you want to be able to learn not just the value function, the updated values for a couple of states, but the entire state space, because that way it would be faster. Okay. Interestingly, if you actually represent, and this is what I was saying at the end of last class, if I actually represent the value function not as an extensional representation, but as some weighted summation of features, and then I would be forced to, the only way I'll go, my reinforcement learning updates now would be essentially modifying those weights. Okay, the moment you modify the weight just so that the current state's value is closer to what you have experienced by executing from that state, implicitly you are also changing the values of a whole bunch of other states. Do you see what I'm saying? Okay, so that's what you got to keep in mind, and then let me just go through the the steps of this. So clearly, if you are really looking at one state by state, there is never enough training data to learn the value functions or the models correctly. Okay, you did do a reasonable job of it in the reinforcement learning project, but that's because it's a very small scenario with very few states. If you have a large number of states, then how long are you going to train yourself before you have any possible approximation to the real model? And if you don't have an approximation to the real model, then how are you going to do the MDP value and false iterations? Okay, so you want to somehow hasten this, and so the idea would be that there is never enough training data, so you have to generalize. So instead of using a large table to represent VRQ, you want to use a parameterized function. Okay, in fact, actually, the ADDs versus the representation we are going to use are basically linear weighted functions, and this is basically here the parameters would wind up being the weights that you are using. Okay, so what is a linear weighted function? It's saying Wi Fi. So if I have a whole bunch of features f1 etc. up to fn, okay, these features can be Boolean. Okay, they can also be real valued, but let's assume they're just Boolean. And so these are the state variables, and you are somehow thinking that there must be some linear representation of the value function over all the state. I mean, the value or policy value function of all the states, over all the states. Okay, so given a state with f1, etc., fn, its value should be representable as sigma wi fi. Now, the only question, of course, is find the right wi such that it becomes as close to the real value function as possible. Now, it is obvious that given any arbitrary value function, you cannot use this representation to exactly represent the value function, right? Because I'm just looking at, it's a very specific form of functions. It's a linear function, okay? And there is no reason why linear functions should be, even though there are infinite number of linear functions, given the infinite different values that you can get for the weights, none of them might be, for none of them might you be able to exactly represent the value function that you have on hand. This is where you are making a big jump. You're just saying, I don't really know what the value function is. I'll jump ahead and assume that the value is just a linear function of the features. Okay? And so then the problem becomes just find the best linear function. The best linear function may still be quite far away. The best linear function might be still quite far away from the real value function. So if you use this linear function to reconstruct the value function, and you have the real value function, and if you take the difference between these two value functions, normally when you take the difference, what do you do? So here is, let's say, v hat, which is the true value function, which says s1 is 0.5, s2 is 0.7, etc. Let's say, let's call this v star. Okay, v star is the real value function, and then v hat is the approximate value function you are learning, and then somehow this approximate value function is some sigma wi fi for some specific values of w's. Suppose I picked up some w's. Okay, based on that, I found that the values here are, this is 0.9, this is 2.3. Okay, clearly this is supposed to be capturing this. It does not. Okay, the question, of course, is what is the difference? The difference is 0.5 minus 0.9 and then 0.7 minus 2.3. Now, normally you don't want to take the absolute differences because sometimes the value could be under or overestimated by your approximation. So you essentially have to take either the absolute values or the square of the errors. Okay, so then the question becomes finding a set of weights such that for those weights the approximated value function is as close as it can be to the real value function. Now it turns out that's exactly what essentially linear regression tries to do. Okay, in linear regression you have an arbitrary function and you are just trying to approximate that function as the closest linear function as possible. Right? Okay, so this is how you go from reinforcement learning to inductive learning. Reinforcement learning was going on in terms of learning the values of the states based on their neighbors. Now this induction is going on because when I try to come close to the current state's value, implicitly I change my approximation for the other states too. My hope is that I'm also coming close to them. Do you see what I'm saying? Okay. So that's basically what function approximation methods in reinforcement learning do. Okay. So the simplest kind of functions, when the function approximation methods depend on the type of function you have, the simplest would be the linear function. Okay. So essentially I'm saying my approximate value function for state S is some parameterized function theta 0 plus theta 1 times the first feature plus theta 2 times the second feature plus theta n times the last feature. Now, by the way, the words feature is basically the same as state variable. Okay, not exactly, but you can almost think that way at this point. Okay, so in this case, these are our state variables, and I basically just converted these state variables. I converted these, I converted these state variables into an approximate value for the state. Okay. So now the question, of course, is can we always define features that allow for a perfect linear approximation? That's the interesting thing. So in fact, actually, the simplest way to think for us coming here is state variables is equal to features. But feature is a more general term. It could just be an arbitrary combination of state variables. So for example, if you have chess, let's say a chessboard, okay, the features could be things like the control of the center, or the number of pawns left on the board, things like that. Those are just features. And so these features, so one way of thinking about it is that there is the state variables representation, and functions over state variables are features, and functions over features become values. Okay. Yes.
Are we assuming that each state is dependent on every state variable?
But the definition of state variables is that each state is specified by providing the valuation over the state variables for that state.
Suppose we have Fn features and one state is dependent on Fn minus 3 and the other one.
No, what do you mean dependent on? It's like these are the properties of the state, and every state has these properties. Do you see what I'm saying? So it's there is no notion of dependency. This is how you describe the state. If you decided that I'm going to describe each state with 10 state variables, let's say, that means every state you should be giving the valuations of those state variables. The only thing I'm saying is features can be thought of as functions over some implicit state variables. Okay, and then you're going directly from features to valuation. Now, if the functions are identity functions, then you are essentially talking directly in terms of individual state variables. If not, it can be arbitrary combinations of features. Now, that's an interesting combinations of state variables. This is an interesting thing. Even though this stuff is linear, and we know that linear combinations, don't necessarily, linear functions don't necessarily have to capture the value function. Okay, now the interesting thing is, basically what we have is the true value function V star is basically, you have for each S1, etc., is H1, etc., Sn, and you have the values for that. Now, imagine that these states are actually defined in an implicit state, in a space of state variables. Let's say V1 to, I shouldn't use the variable, SV1 to SV, K. So there are K state variables. Okay, now the features are functions over the state variables. And the value approximation is a linear combination of features. The leeway I gave myself is I didn't tell you exactly how I defined the features. What if I define the features are nonlinear combination of state variables? And then you take linear combination of nonlinear combinations. Then I obviously have a lot more expressiveness than I let you think. Did you understand what I'm saying? So this is the question. Can we always define features that allow for a perfect linear approximation? For this question to make sense, features cannot always be just the state variables. If features are always state variables, then I can pretty much right away say, of course not. Okay, but if on the other hand, I can define features as arbitrary functions over state variables, then it is actually possible. It is actually possible to come perfect linear approximation. Okay, the idea would be to say the feature would be the state name. I can define features in such a way that this feature will be 1 for state S1 and 0 everywhere else. And then similarly, F2 will be 1 for state S2 and 0 everywhere else. You see what I'm saying? The moment I do that, now I essentially have exponential number of features. But then clearly, I would be able to find exact approximation, exact representation for the value function. Did you get what I'm saying? So because if let's say S1 is 0.3 and Sn is 0.9, then I would just say 0.3 times F1 plus 0.9 times Fn. And remember that F1 will only be 1 for the first state and 0 everywhere else. And Fn will only be 1 for the nth state and 0 everywhere else. So I would have exactly captured the value function. Okay? Just a second. Now, the trick, of course, is that's not a smart idea because you just have way too many features. The whole point of going factorization is to be thinking in terms of a space that is smaller than the number of states. Now it's bigger. Okay? So now what we'll do is, of course, so because of that, you would essentially look for smaller number of features, and so you'll never be able to get full capture of the value function, but you can find the weights that will get you as close to the value function as possible. To do that, you do gradient descent. Okay, there's a question.
What's a good way to approximate value or reward function if the state variables are made up of different types of variables, like booleans and floats and integers, and it's just a big map?
How does it matter? There are numbers to me. I'm not sure what your question is. So you decide. So the thing is, here the fact that we are deciding what features are basically brings up this dirty word that nobody speaks of in machine learning, which is feature engineering. Okay, and basically, the state variables. Okay, think about this. Actually, by the way, this discussion, although I'm doing it in the context of reinforcement learning and factored approaches, it flows directly into the rest of the semester's discussion on learning, for Bayes networks and so on, and in general machine learning. Okay, so let's think for a minute about, I'm talking about state variables and features. It's sort of wishy-washy, right? What exactly are the state variables? What exactly are the features? Okay, maybe you had some idea, but maybe you're not. Consider the following scenario. Suppose it turns out that I'm trying to write functions over images. Some image. Turns out it's a 256 by 256 image. And let's make my life simple. Let me assume that the pixels are on or off. Right? Okay. I would argue that the state variable representation, which is completely lossless for this picture, is 256 by 256 Boolean variables. There is no possible way you can, somehow bring in more things into the image than there are in the image. And 256 by 256 Boolean, pixels are the only things that are there. So I would call them the state variables. Any approach on image classification or image reasoning that directly works on 256 by 256 is going to die here itself. But now, you guys are, crazier and crazier. So we are normally talking about 1960 by 1024 with 64 values per each bit. So then that is the actual number of state variables. You change one particular pixel's value, the brightness from 63 to 62, it's a completely different picture. It's a completely different picture because its state variables have changed. One of them has changed, so it is a different state variable.
Basically, it's a new state.
What? It's a new state, right? And imagine you're trying to do some learning over these features, these particular images. If in fact this learning function depends on the, it's going to take into account every pixel value, you are dead on arrival. Because you would wind up needing a humongous number of images to train yourself to get anywhere close to reasonable performance. So instead, you would then define over these state variables, you will define features. Features might be things like average grayness, the number of edges, things of that kind, which are arbitrary functions of the lower level state variables. And you come up with these features, and then you give it to your favorite machine learning algorithm. And most of the time, the difference, if you come up with the right features, the learning algorithm makes less of an important, is not as important if you can come up with the right features. But then if you come up with the right features, in some sense you're cheating. You know approximately what to look for in analyzing these images. So that's the reason why feature engineering is like basically, it's in the background in machine learning all the time. If you kind of come up with the right features, then you can always find even the simplest learning algorithm would be able to solve, learn something. Okay, so that's the point that we are making here, that if you, as I said, if you can always define features that allow for a perfect linear approximation. One way is assign each state an indicator feature. The indicator feature would be 1 for that state, 0 for everybody else. Then of course you will be able to find a linear combination over these. Right? Linear combinations over these such that it would capture the value function, any arbitrary function over the states exactly. If not, I can always come up with scenarios where the approximation you are trying to do comes close but will never be exact. Okay? Anyway, so here are some examples of the features that we are using in the grid scenario. So we are essentially talking about, I came up, basically the value function for S, we are writing it as 10 minus x minus y. Okay, let's say if I do it that way, then in essence, it will give you values for various, states. That's one, representation. Okay, so in general, you have theta 0 plus theta 1x plus theta 2y, where you are assuming that the features are the same as the state variables in this case. You're not considering any higher level features. See, this notion of higher level features is what allows you to go from state variables into nonlinear combinations of state variables, and then you can do linear combination over them. Okay, so right now, to make my life simple, I'll just assume that I'm just basically directly doing linear combination of features where features themselves are state variables. Okay, so then the question would be, which should be the values for theta 0, theta 1, and theta 2 such that this captures the true value function. Okay, normal inductive learning would have the property that it would give you V star, which is a big table. Okay, and then it asks you to find Vs that closely approximates this V star. Now, I don't know if you people thought about this. There is a strong connection between learning and compression, right? Learning and compression. From the compression point of view, lossless compressions are good, lossy compressions are bad. From learning point of view, good learners typically are lossy. And that should make sense to you based on the discussion we just had. Okay, good learner always would be lossy in the sense when you reconstruct, you basically will never be able to capture the value function exactly. Okay, and if you're trying to do lossless compression, okay, then you would need to do a lossless compression on V star, you would need the entire V star function. And after showing it to you, then you're just compressing it. This is what you do in, what's the difference between image compression and image classification, let's say. In image compression, the entire image is given to you. At some point of time, you represented the entire image in your computer. And then quickly convert it into a compressed version. Okay. Here, so in some, whereas in the, in learning, you would like to basically be able to get by with just part of the V star, some part of the true function V star, and then still find theta, theta 0, theta 1, theta 2, which not only would be close to the parts of the V star that are shown to you, but it will also be close to parts of the V star that are not shown to you. In the learning terminology, what's the difference between the part that is shown and the part that's not shown? Training and test. Nobody talks about training and testing in the context of compression. In learning, there is. The reason is you never really want to deal with the entire V star and compress it. You want to just look at part of V star and compress it. And find an approximation for that, which would somehow be good for the rest of the V star too, that you haven't seen. Okay. Okay, so so now the question, of course, is this is basically the if I give you, let's say, if I give you a particular form for the approximation, theta 0 plus theta 1 f1, etc. up to theta 1, theta n fn, where I tell you how f1, etc., fn are defined in terms of the state variables. Okay. Now my question is, and I give you some examples of V star for certain states. For the states that I tell you, I know their feature values and I know the value function, the true value function. That's the training data. Now what you're trying to do is set these theta 0 up to theta n in such a way that this function not only is close to the stuff that I've shown you, the training data, but also would be close to the stuff that I haven't shown you, the test data. That's what learning is all about, right? Okay, so now, and in some sense, if I figure out how to do that, then I can say that that same idea can also be used as a subroutine in reinforcement learning. We're going now back to reinforcement learning. In reinforcement learning, where in essence, so for example, if I give you a bunch of training examples, right, and then you can do learning. But if I give you training example one by one, you still can do learning. That's incremental learning. In reinforcement learning, each time you behave, you get an extra training sample about the closer value, the true closer approximation of the true value of the state you are in. Okay, and then using this, you want to change your representation, this representation. The way you want to change this representation would involve, you can't change the features for the states. That's given. The only thing you can do is change the thetas. So the updates in the reinforcement learning now are not going to be the value update directly, but the theta updates, which will then change the value. But then they not only change the value for the states from where you actually executed, from where you behaved, but because you change the thetas and the thetas are shared by all the states, in effect, you're also changing your approximate values everywhere. That's a bug or a feature, depending on what you say. And we see it as a feature because, in a sense, we are now able to get closer, hopefully, to the value functions in the other parts. Okay? So now this, having said this, the question, of course, is then how do you change the thetas? This is just like the technical, heart of how do you do basically linear regression. Okay, and one basic idea which will keep coming for the rest of the semester is gradient descent. Okay, because it turns out that in a minute we'll show that we can set up what we are trying to do as minimization of an error function. And this error function turns out to be a multivariate error function. It's a multidimensional error function, and it's continuous. It's continuous in the space of what? I didn't tell you that features are continuous. We are talking about error function being continuous in the space of thetas. As you change thetas, the error function changes. Now you're trying to find the configuration of thetas where this function will be the smallest value. And obviously, if you are just done computer science undergraduate study and nothing else, you have forgotten your calculus because you never had to use calculus in undergraduate computer science. You had to do discrete math. But before that, obviously you knew continuous functions and minimizing and maximizing continuous functions. What do? You take basically remember the derivative test, okay, and the second derivative test, okay. And in general, right now we are doing function minimization when the function is multivariate. So you then take the partial derivatives over all the thetas, set them to 0. That'll give you a critical point. Now just because, and that critical point could be a local minima or a local maxima, depending on the error function. So it could be a local minima or a global minima, depending on the error function. Okay, and then we'll just hope that most of the gradient descent will at least get you to the closest local minima in the error function. And they'll say that will tell you, they'll tell you now that these are the values of thetas for which the function is at a local minimum. Now the question is, if you remember doing this, I'm sorry if I'm boring people who have been doing gradient descent for a living. I know some of you might be in machine learning, might be doing it all the time, but I'm also thinking of other people who don't do gradient descent much. Okay, so one thing I want you to think of is the time when you did gradient descent for single variables, right? You would get the df by dx, okay, and then you will get an expression. You will equate it to 0, solve it, right? We wouldn't call it search. We just call equation solving, right? Okay. So why is gradient descent? We'll see that gradient descent is actually considered a search, and the reason gradient descent is considered a search is actually that, first of all, if you have multivariable scenario, multivariable function, then you don't have a single function. You don't have df by dx equal to 0. You have dou f by dou theta 1 equal to 0, dou f by dou theta 2 equal to 0, etc. So each of the partial derivatives is set to 0. Now these partial derivatives, first of all, can be linear or non-linear expressions on theta. And you have a whole bunch of them. So you are talking about at least simultaneous equations, and it could be simultaneous non-linear equations. And you just want to find the solution to this simultaneous nonlinear equations. It turns out that finding solution to simultaneous nonlinear equations isn't easy. And Newton's method comes in handy. Newton-Raphson method comes in handy. And Newton-Raphson basically said, well, if you have a nonlinear functions and you need to find the roots, then just do gradient descent. So take a little step in the direction of the local gradient and then reevaluate everything. Okay, I'm going to show this here, but the reason I'm going into this, even though this is not really just about reinforcement learning, most of the differences in learning for, let's say, Bayes networks ultimately boil down to the technical differences in whether or not certain Bayes network learning problems will lead to simple simultaneous linear equations, coupled simultaneous linear equations, coupled simultaneous nonlinear equations. By simple simultaneous linear equations, I mean the first one will give you the value of x itself. Then you substitute that in the second one, you will get the value of x, y. Then you substitute that in the third one, you'll get the value of z, and so on. It's already sort of a diagonalized one. That would happen, for example, if each partial derivative is in exactly one variable. Everybody else dies. Then you will essentially get decoupled partial derivatives. And if they're linear, then you're done right away. If they're nonlinear, it's still painful because you now have to solve nonlinear equations in single variable. Okay? And then next, of course, you can have true simultaneous equations. And then you can have true simultaneous nonlinear equations. And as things go this way, then actually coming up with the right gradient descent algorithm becomes painful. And so there is an entire branch in mathematics, essentially continuous function optimization for multivariables, which we never touched even if you did calculus 3 in your high school or as part of your engineering. You would have probably gone to 3 or 4 dimensions. And you did not have to think about all the crazy things that can happen when you're trying to A, get a good representation for the gradient, and then B, evaluate the gradient locally and then make steps in that direction. Okay, when I say it that way, basically the whole point is to lose the magic between multiple different machine learning algorithms. So for example, when you go to the Bayes networks, we'll see that there are cases where Bayes network learning is extremely simple. Those are called complete data scenarios. Okay, and it turns out the reason it becomes extremely simple is because each of the partial derivatives would be in terms of exactly one variable, and it's a set of decoupled linear equations. And then when you have incomplete data, that means, in the Bayes networks, when you have incomplete data, that means you have variables whose values are not given in the training data. Then it turns out that the equivalent gradient descent now would not have this nice property that, partial derivatives would be decoupled. And you can actually do, normal, gradient descent in that case, but there's also this idea called expectation maximization algorithm, which we'll talk about, which turns out to be just a gradient descent tailored for Bayes networks. Okay, so I sort of thought I'll spend this much time here so that you'll get gradient descent back into your head. If you've been doing it for a living, good. If not, bring it back, because that's what we'll be caring about. And the difference between multiple different learning scenarios would be which one has easier gradient descent. You see what I'm saying? It looks kind of very non-romantic. You would like learning algorithms to differ in bigger things than just the ease of finding the gradient, but that's ultimately what we're talking about. Okay, so basically, I want to update theta, and this is essentially what I've been saying in the background, that this is the background on multivariable function minimization. So you can get a gradient of a function of theta, where theta is theta 1 to theta n. That means n, variable function. The gradient is essentially this set of partial derivatives. And you can evaluate it at that particular point. Remember, the point theta is given by theta 1 to theta n. Okay? And you can evaluate the gradient at that point, and you'll get this vector. And you're making steps in the direction of that vector. That's what gradient descent is going to do. Okay. Now, why is gradient connected? This is basically the point. This is just going back to your calculus. So we start by taking the true value at each state minus the value, the true value at each state, which is VSJ, minus the value that my approximation tells me is the value for that state. And I take the difference, square it so that whether it's upper or lower, it's both bad. Okay, I square it, and then I throw in a half, because if you minimize the half function, then you also minimize the real function. By the way, we'll play this game a lot, okay? One of the things about function minimization is to minimize one function, you can minimize another function. And they may not look the same at all, but they both will have the same point where they become minimum. Do you understand what I'm saying? So I can have, so if you consider a function which is just this, and another function which is this, they actually have the same shape, but one is below the other. Okay, but I can even have situations where one function is sort of like that, another function is like that, and then they both still have maximum at the same point. In general, in fact, we do this a lot in Bayes networks, because one of the things, what's the normal operation in arithmetic that you should be happy about? Addition. If you're not happy about addition, we are in big trouble. Okay. In probabilities, what's the normal operation that you should be happy about? Multiplication. I mean, I hope you'll get that, but if you remember your elementary probability theory, the best that can happen to you computationally is everything is independent of everything. In which case, all probabilities are multiplications of probabilities, smaller probabilities. So if you're lucky, you get multiplications in probabilities. But it's so much simpler to minimize functions which only are additions rather than multiplications. So one thing that we will do in Bayes networks is we take a function that is like, that is represented as a product of a huge parameterized set of probabilities. Take the log. If I take the log, the multiplication becomes addition. You see what I'm saying? And then you essentially maximize the log likelihood or minimize the log likelihood. And it turns out that when you do that, you are also maximizing the original function, because logarithm is a monotonic transformation. You see what I'm saying? That's exactly, this half, right now this is half, little later we'll put log. That's fine. And you shouldn't, think where the heck is this stuff coming from. It's basically, we are only looking for the minimum point. Once I know the point, finding the minimum value is simple. In fact, we are much more interested in the place where the minimum occurs than the value at the minimum, oftentimes. Okay, so anyway, so I threw this half in, some of you probably would know why I threw this half in. Why? If you remember, if you have x squared, then you differentiate it, you'll get 2x. And if you have a half sitting, they'll get cancelled out. For the life of me, I couldn't quite understand why it's important to cancel that half, but typically people write this error function with the half thrown in. Okay, so now you have this, but this is fine. You don't mind, if you are minimizing half the error, then you're also minimizing the real error, right? Okay, so the question then is, how do I minimize this expression? Now, the point to remember is this expression is the variables in this expression are the thetas. Remember, the VSJ would be a number, so I would have given you some training data which says for S1 this is 7, S2 it's 55, etc. So those would be the numbers I'll be putting here. And this is some current theta 1, theta 0 plus theta 1 times F1 plus theta 2 times F2, etc., theta n times Fn. And then I know the current values of thetas, and then I know the features, I throw them in, I'll get this value. And I'm basically taking the difference. So in particular, if I'm actually starting without knowing the thetas, then this expression would be an expression that varies over the theta values. Okay, varies over the theta values. And all I then need to do is minimize this, and to minimize that, basically the gradient descent tells me that if I change each ith theta, ith parameter, by shifting it a little in the direction of its gradient, okay, And the amount I'm changing it by is alpha. Amount I'm changing it by is alpha. And by the way, in this particular case, we are minimizing the function. And if you look at a function like this, and you are here, and you want to come here, this is the minimum. Okay, the gradient is going to be this direction. It's raising. So you need to turn around. That's why the minus. Right? Okay, so the gradient vector would be telling you the direction of increase of the function. And if you're trying to minimize, you want to go the opposite way. If you want to maximize, you go that way. And now the question, of course, is how big a step do you make? Alpha is the learning rate. If you make small steps, then you'll take forever to get to the minimum. If you take large steps, you will overshoot the minimum and go a different direction. And then there is an entire, cottage industry of, either starting with something, currently for all these algorithms, alpha is basically a hyperparameter. People assume that some alpha is given. That's their learning rate. Okay, so if you write a gradient descent, algorithm, you'll say I set alpha to be say 0.5. You could also do better than that. You can say that in the beginning, alpha should have high values, and as you come closer, the alpha should have smaller values. Okay, there are gradient descent techniques that basically change the alpha as you keep taking steps, so that when you come close to the minimum itself, you will make smaller steps. Okay, but notice already that even if you have a fixed alpha, when you come close to here, the gradient will always be already be close to 0. So however big your alpha is, for the same fixed alpha, the step size was bigger here and smaller here. So there's already that built in the gradient descent, because when you come close to the minimum, the gradient is close to 0, so you'll make small steps. But there are also algorithms which will actually try to basically put a schedule on how the alpha is changed. Okay, fine. So in this particular case, I'm just going to do this, and then I want to differentiate this with respect to theta. Okay, differentiate this with respect to theta. However, notice that dou E by dou theta is the E is in terms of V theta is in terms of theta. So you basically do chain rule of differentiation. If you forgot chain rule, I cannot get you all the way back to beginnings of the civilization. So you have to remember the chain rule. Okay. All chain rule says essentially is if you have 2 log square x and you're trying to differentiate it, you first differentiate this part, so it will become 2 log x, and then you differentiate log x with respect to x. So you differentiate this entire thing with respect to log x itself, so you get 2 log x, and then you differentiate log x with respect to x, you get 1 by, thank goodness. Right? I mean, if you don't know log x differentiation, we'll be in trouble. Okay, because that's what I told you I'm going to take logs everywhere next week. So that's basically what you do. Okay, it's kind of nice that when they force you to do continuous math, despite your pleas that I'm going into computer science, why do I need continuous math? You still have to use it now. Finally. Okay, so that's what basically you do, and once I get so basically the reason this happens is, notice that you have square of this whole thing. So this is like log x. So square, so 2 times this, and the 2 gets cancelled. And then I need to differentiate the inside one with respect to theta. Now when I differentiate the inside one with respect to theta, this guy goes to 0 because this doesn't vary with respect to theta. This guy does not go to 0, but this guy is actually a linear function of theta 1, theta 2, etc. So when I differentiate theta 1 times, 2 theta 1 plus 3 theta 2 with respect to theta 1, what do I get? Just 2. Because the 3 theta 2 is constant with respect to theta 1. So what I wound up getting is just the 2, which is the coefficient of theta 1. Now what is the coefficient of theta 1? Feature 1. It's funny, I mean, if you look at it from the feature point of view, thetas are the coefficients of the features. If you look at it from the theta's point of view, features are the coefficients, right? Okay, so that's basically what we did. And I'm going through this in this ridiculously slow rate, not so much because this was invented as part of reinforcement learning, but this happens to be the first time we are talking about basic gradient descent. We're doing it with respect to reinforcement learning, but we will do it with respect to everything else next class. I mean, like base networks next class. So that's why it's really what it is. So now I know the function, the feature value at that state, and I know the difference. I know the difference, right? And then I know the alpha, so I get to change theta a little in the direction. I nudge it towards its correct value. Okay, now notice, of course, that where in this whole thing did I say, I mean, is it clear that I will never be able to capture the value function exactly? This is just a sanity question. I did all this, right? And then I'll find the thetas, which is supposed to be the configuration of thetas, which is the best representation of the value function. Now, why did I say, why is it obvious? I mean, why should you believe that at that point the fit won't be exact?
Because the gradient with time is getting closer to 0, so the whole value will converge as to that.
No, it's much simpler. This is just, yes, sir.
You don't have enough for the right features.
No, I'm not saying, this is a sanity question, okay? So I found the theta values that minimize this. And I said that would be the theta values I use to approximate the value function. And I'm saying there is no reason to believe most of the time that the approximation will be exact. Why?
Because we're taking square of the errors?
No, not just that. The function minimum doesn't have to be 0. The function minimum doesn't have to be 0. Okay? So, since you seem not to be convinced about this, I now show you how psychologists find lines in any possible set of data. Actually, there's a funny, I'll try to find that article and show you how to find lines irrespective of what actually the data is. Okay, so of course, if I have data like this and then I find the best line fit, I find that's not going to be exact, right? There is points that are far away. So there would be some error. It's not error, not going to be 0. If the original points are actually on this line, so what I'm trying to say, I hope you understand, is if my original data is this, that's my data. Okay, I can still be stupid and find this looks like a good line for that data. Right? That means I don't know how to do gradient descent. Okay, but if I do gradient descent, I'll find this as the line. Right? Okay, but what if my original data is like this? A nice sine wave on the diagonal. Suppose you give this to a line fitting program. What do you think the line fitting program will say? Sorry, you gave me the wrong data. It's a sine wave. I shouldn't be dealing with this. That's what it says? No, it'll find a nice line. There you go. And it turns out that would be the line that has the least error. Okay, if you don't do the gradient descent correctly, then you might find a line like that. That shows you're stupid, in the sense your algorithm is stupid. This is the best line for this data. when you got this line to represent this data, you still have a humongous amount of error that's left. You just minimize the error. Between this and this, you chose this because you minimize the error. Okay? Okay, so once you understood this, then essentially I'm saying this is basically the batch version of function minimization. So I give you all my training data up front. Okay, then I get to compute, basically with respect to the training data, I get to compute my full error, and then I can just make steps directly, in that error space until I get to the minimum of the error. A more interesting version is the incremental learning, where I give you the true function piece by piece. So I'll give you first 10 values of V star. And then I'll give you the 11th, then I'll give you the 12th, then I'll give you the 13th. So more examples came. That's incremental learning. And all I want to say is in reinforcement learning, you essentially have incremental learning. Now the interesting thing, of course, is if I gave you 10 values of V star first, then I gave you another 5, right? One thing you could do is I can basically first, when I had 10, I will find like a function for representing this, capturing this best. And then when I got 5, I can redo the whole thing with 15. Start from scratch. That's one way. The other way is, by the time I came to 5, I no longer have the old data. The whole point is, if you are combining compression and learning, when you got 10 data points, I compressed it already into my learned representation. So I only have the approximated version of these 10. And then to it, I add extra 5 real ones. And then I do learning on that. And that's basically what good incremental learning algorithms do for efficiency reasons. Otherwise, you have to keep every training sample you ever saw in your life separately in your head while you have your classifier also, which sort of defeats the entire purpose of learning. You remember all the cases as well as the generalization. You see what I'm saying? Okay. So in the case of incremental learning, the general thing what you would wind up doing is, whatever at this point the value, your best approximation to V star is the function you have learned. And then you're just going to change that function using the theta values of that function, changing the gradient, using the gradient descent. Okay, so if you do this, then in essence, basically, you have, in this case, you have linear, reinforcement learning with linear function approximators. And that's been quite helpful in reinforcement learning applications because it increases the efficiency significantly. Now, of course, the question is whether or not it's going to be good depends on whether or not you got the good features. Whether or not it's going to be good depends on whether or not you got good features. You know that if you have 2 power n features where n is the state Boolean variables, you can always be good in the sense of exact capture. But otherwise, you would still, all the gradient descent will do is get you to the minimum in the error function. Depending on your feature space, the minimum error that you have could be particularly bad. Okay, so one last thing I want to mention, actually, although we are running out of time, is that if you have these sort of factored representations. Until now, we had factored representations for the value function in the reinforcement learning. Now, one interesting thing is, why not have a factored representation for the policy function? And in the case of reinforcement learning, instead of first learning the value function and then converting it to the policy, you can say, to heck with that, I'll just go directly and find the policy. Now, the interesting thing there then would be that you start with a policy pi and you tweak it. Now, just as to tweak V, you needed to represent V in a parameterized form in terms of some thetas. So instead of representing value in the parameterized form, you want to represent the policy in parameterized form. Okay? And if I have given you a functional representation of the policy in a parameterized form, then what I can do is I can do gradient descent in the policy space to find the policy where the reward is the best. Okay, what did I say? Gradient policy. So, not surprisingly, there is an algorithm called policy gradient algorithm for reinforcement learning, which directly does local changes to the policy. The thing that I want you to understand is when you talk about local changes, meaningful local changes, either for value or policy function, require parameterized representations of the functions. You are doing local changes, even in the extensional case, but the local change would just change one state's value. That way it will take forever to get anywhere doing local search. Here you are essentially having a parameterized representation for the policy as well as the value function, and then you make tweaks in the case in the parameters to come up with different policies. Okay, the only interesting thing, and there is actually a lot of neat stuff about how to how do you change the policy. Basically, for each policy pi, there is a value for that policy. For the policy pi theta, there is a the cumulative reward you would get by running that policy. Remember, long back, before we went into MDPs, we said, if I give you policy 1 and policy 2, which is better? You can empirically determine this. Run this policy for a while, see what is the expected cumulative reward. And the one which gives you higher cumulative reward is the better policy. So I really want to think in terms of rho theta, which is the expected cumulative reward returned by a policy. If I change pi theta, rho theta changes. And the interesting thing is pi as well as rho are dependent directly on theta. They are functions of theta. Right? And now I want to do gradient descent in the space of rho theta, on the function rho theta, to find, in this case, maximum, not minimum, thus plus. In the gradient, it's called gradient ascent, not gradient descent anymore, because we want highest return thing. Everything looks fine and dandy. You just now do gradients on the policies, etc. The two big issues. Okay, one is rho theta a function that is differentiable? You forgot about this. Most of you forgot about this whole idea. Right? Those of you who deal with this still, that's great. But most of you never, any longer care about when a function can be differentiable. Right? A necessary condition for the differentiability of a function is what? Continuity. So it's a necessary condition. The function has to be continuous so that it is differentiable everywhere. Okay? Now, if you have a policy, the kind of policies we look at, basically, let's say you have two actions, A1 and A2. And this is, the Q value from state S for A1. This is Q value from state S for A2. This looks suspiciously like our POMDP stuff, right? The POMDP value function was not differentiable. It's piecewise linear. Now we are not talking about POMDP, but we're talking about the policy directly. Now the policy sort of just, at this point, it goes from A1 to A2. Now, it may well be that up until this, it will take A1, and then after this, it will take A2. The reward for A1 might be this, reward for A2 might be this. So right at this point, the reward fell nicely this way. This is the kind of functions that your math teacher said you should hate, right? Because these are discontinuous. How can I do gradient descent when I have discontinuity? Again, this is the idea of what is this, the tail wagging the dog. Okay, it's like gradient descent is the technique that we are supposed to be interested in to solve a bigger problem. But gradient descent says, I won't work with you unless you give me continuous functions. So I will change my life around so that I can use the technique. Looks very weird, but that's exactly what we'll wind up doing. So I need a policy which would be, a representation of policy which would be continuous. Long back, we talked about mixed policies. A mixed policy, even MDP is stochastic, right? So original idea would be that in a state, there is a probability distribution with respect to which you are supposed to pick an action. And then I pointed out to you that even though that is what we might expect, which is the mixed strategy, for any normal single agent MDP, if there is an optimal policy, there is also an optimal non-mixed policy. I forgot the name for the non-mixed. That means you just pick an action in every state. There is a single action in every state, right? And I did give you the exception. The exception is when you have multi-agent scenarios where you need to have mixed strategies, because if you play rock, paper, scissors with one single strategy, you die, right? Now I'm going to come back and say, let's go back to mixed policies. Remember, mixed policies were not thrown out. All I said was, if there is an optimum in mixed policy, there is also an optimal non-mixed policy. Mixed policies are continuous because mixed policies will combine two discrete entities with probabilities. So policy gradient algorithms, and this is the reason I want to bring this up, the policy gradient algorithms essentially bring up mixed policies. What they'll do is they will, instead of picking the action, they will provide the probability of picking the action. Previously, you pick the action based on whichever Q value is the highest, just max. Now you convert it into a probability distribution. You say it's essentially an exponential, the probability is an exponential distribution that is proportional to the Q value of the action. The higher the Q value of the action, is higher probability that you would pick it. You would not be required to pick it. It's just higher probability. The moment you do this, the rho, just as, so this phi theta is a mixed strategy now, mixed policy. So you can have rho for this phi. That would be continuous function. And I then do gradient ascent in that mixed strategy space. I find this fascinating at some level because this is completely the technique, the tail wagging the problem, the dog, right? We never really said the policies are supposed to be. We know that for these problems there is a single policy. I mean, you don't need mixed policies. But to find that, you actually need to, you are better off going through the space of mixed policies because those are continuous and so you can do gradient computation. The next several slides, which I won't be able to show, tell you how to actually compute this gradient effectively. And once you do that, the reason this is all interesting is, if you remember, is that actually this is the idea that was used to train this the inverted helicopter, for example. There, that one. It's inverted helicopter, training is a reinforcement learning function problem, and they essentially train this with respect to a simulator using policy gradient approach. And typically, what happens is when policies have much simpler representations than the corresponding value functions, okay, policy gradient turns out to be a better idea than TD learning. Okay, there's a lot that went on here. One is that reinforcement learning, we always just only did value-oriented methods. We didn't touch the policy-oriented methods when we did normal reinforcement learning. Now I got you the policy gradient, which is a local search in the space of policies. Okay, but I only talked about it in the context of parameterized policies, because local changes don't make sense. Non-trivial local changes cannot be done unless the function is parameterized, because otherwise you just change the function at a point at a time and you die. Okay, but much more than that, back of this whole discussion is this whole thing about gradient descent and gradient ascent, and how just to be able to use gradient descent, we are willing to change our problem. Okay, this keeps coming up in the next several lectures when we talk about Bayes network learning. Okay, so I'll see you on Thursday and take your questions on Bayes networks, and please help yourself with more raspberries. Wednesday, yes.